Have you ever wondered how scientists separate mixtures in the lab? Today we dive into the fascinating world of chromatography. Chromatography, a term derived from the Greek words for color and writing, is a powerful tool in the scientific world used to dissect complex mixtures into their constituent parts. Its purpose is elegantly simple: to separate. But the ingenuity behind it and the impact it has on various fields of study is anything but simple. Imagine a crime scene where a suspicious substance is found, or a medical lab testing a blood sample for a rare disease, maybe even a food safety lab verifying the ingredients in your morning cereal. In all these scenarios and countless more, chromatography plays a vital role. At its core, chromatography involves a stationary phase and a mobile phase. The mixture to be separated is carried by the mobile phase, typically a liquid or gas, over the stationary phase. Depending on their affinity for the stationary phase, different components in the mixture travel at different speeds, thus achieving separation. Now, there are several types of chromatography techniques, each with its unique approach. Column chromatography, for instance, uses a column filled with the stationary phase, and the mixture is poured in at the top. The components then trickle down at varying rates, separating as they go. Gas chromatography, on the other hand, uses a gas as the mobile phase and a coated glass or metal as the stationary phase. High-performance liquid chromatography, thin layer chromatography, paper chromatography. The list goes on, each with its unique features and applications. But why is this all important? Well, without chromatography, many scientific discoveries and advancements would not be possible. It's a cornerstone of analytical chemistry, providing invaluable insights into the substances that make up our world. With this, we've set the stage for our journey into the depths of chromatography. Chromatography is not just a fancy word, it's a complex process based on a simple theory. Now let's plunge into the basic theory behind chromatography. The heart of chromatography lies in the interaction between two phases: the stationary phase and the mobile phase. Imagine the stationary phase as a silent observer, sitting still while the mobile phase moves right through it. The stationary phase can be a solid or a liquid, while the mobile phase is a liquid or gas that carries the mixture of molecules we want to separate. Here's where the magic of chromatography happens. Each molecule in the mixture interacts differently with the stationary and mobile phases. Some molecules feel more at home in the stationary phase and tend to stick around, while others prefer the moving company of the mobile phase. These differences in affinity create a beautiful dance of separation as the mixture moves through the stationary phase. Now let's picture the process in our mind's eye. As the mobile phase carrying the mixture flows over the stationary phase, molecules start to separate. Those with a higher affinity for the mobile phase move faster and travel further, while those favoring the stationary phase linger behind. Over time, this leads to a clear separation of the molecules. It's like watching runners in a marathon, each moving at their own pace, gradually spreading out along the course. But wait, there's more. The distribution of molecules is another crucial aspect of chromatography. It's all about how the molecules distribute themselves between the stationary and mobile phases. This distribution coefficient, as it's called, is a major factor influencing the degree of separation. The higher the difference in distribution coefficients of two molecules, the better they will separate. In a nutshell, chromatography is a delicate balance of interactions between stationary and mobile phases, and the unique characteristics of each molecule in the mixture. Understanding these basics paves the way to delve deeper into the various types of chromatography. So stay tuned as we unravel the intricacies of this fascinating process. One of the most common types of chromatography is column chromatography. This technique is all about separation. Imagine a bustling crowd at a concert and you're trying to spot your friend. Well, column chromatography is like the security guard who helps you find your friend. It separates a mixture into individual components, making it easier to analyze each one. The principle behind it is simple. It's all about the dance between stationary and mobile phases. The stationary phase is packed into a column, and the mixture to be separated is carried over it by the mobile phase. As this happens, different components in the mixture interact differently with the stationary phase, causing them to travel at varying speeds and separate. Now, packing the column is an art in itself. The packing material, often a solid or a liquid on a solid support, is chosen carefully to interact selectively with the mixture's components. Column chromatography, with its unique characteristics, is a powerful tool in a chemist's arsenal. The efficiency of column chromatography is not a game of chance, but a result of meticulously calculated variables. Now let's delve into the heart of column chromatography efficiency: the Van Deemter equation. This equation is not just a mathematical formula, but a unique tool that helps us understand how different factors impact the performance of our chromatographic column. The equation itself is elegantly simple. H equals A plus B over U plus Q. Here, H, known as the height equivalent to a theoretical plate, is a measure of column efficiency. A, B, and C are constants, and U is the linear velocity of the mobile phase. The first term, A, is the eddy diffusion term. It represents the impact of multiple paths that molecules can take through the packed column. The second term, B over U, is the longitudinal diffusion term. It accounts for the fact that some molecules move faster or slower than the average velocity, causing them to spread out over time. The third term, Q, is the resistance to mass transfer term. It reflects the time taken for solute molecules to equilibrate between the mobile and stationary phases. As we increase the velocity of the mobile phase, represented by U, the B over U term decreases, while the Q term increases. This leads to a U-shaped curve when we plot H against U. The minimum point on this curve represents the optimal velocity that maximizes column efficiency. But remember, each term in the Van Deemter equation depends on the properties of the column and the solute. This means that by carefully selecting our column material and operating conditions, we can optimize these factors and improve the efficiency of our column. The Van Deemter equation, therefore, is a cornerstone in optimizing the process of chromatography. Understanding and applying it can help us make the most of our chromatographic systems, whether we're separating complex mixtures in a lab or purifying a product in a large-scale industrial process. The success of chromatography doesn't rest on the column alone. Other factors come into play as well. One of these critical factors is the capacity factor. This factor, also known as the retention factor, is a measure of how long a solute is retained on the column. A higher capacity factor implies that the solute spends more time interacting with the stationary phase, which can enhance the separation efficiency. However, if the capacity factor is too high, the solute might take too long to pass through the column, which can lead to peak broadening and a reduction in column efficiency. So it's about finding that sweet spot, not too high, not too low. Another important parameter is the resolution, which measures how well two peaks are separated in a chromatogram. The greater the resolution, the better the separation. Then we have the selectivity factor, which reflects the difference in interaction between two solutes and the stationary phase. A high selectivity factor means that one solute interacts much more strongly with the stationary phase than the other, promoting separation. Lastly, we consider peak symmetry, which relates to the shape of the peaks in the chromatogram. Ideally, peaks should be symmetrical for accurate quantification of the solutes. These factors, when optimized, ensure the effective separation of components in a mixture. Chromatography isn't just a laboratory technique. It has real-world applications that impact our lives. Let's explore a few of these. Imagine you're a scientist working on a new drug. Before it hits the market, you need to ensure its purity and determine its components. Chromatography can help you with that. It's a critical tool in pharmaceuticals, enabling the separation, identification, and quantification of components in a mixture vital for drug development and quality control. But this technique isn't confined to laboratories. It ventures into the great outdoors too. In environmental monitoring, chromatography helps scientists detect pollution levels and identify pollutants. So every time you hear about air or water quality reports, remember, chromatography probably played a part in that analysis. And who doesn't love a good meal? But have you ever wondered about the safety and quality of the food you eat? Chromatography is your silent guardian. It's used in food testing to identify additives, pesticides, and other harmful substances. So from ensuring your apple is pesticide-free to confirming the authenticity of that expensive bottle of wine, chromatography is there, working behind the scenes. Chromatography also finds its way into forensics, where it aids in solving crimes by analyzing substances found at crime scenes, and in the petroleum industry, where it helps in the analysis of crude oil and its derivatives. Chromatography, in its various forms, plays a pivotal role in numerous sectors, making it a significant tool in scientific research and beyond. So, that was a whirlwind tour of chromatography. We've delved into its basic theory, explored column chromatography, dissected the Van Deemter equation, and examined system suitability parameters. Remember, the art of separating mixtures is key in many scientific endeavors. Subscribe for more because you won't find me later. Stay curious, keep learning, and until next time, keep exploring the world of science.